Now let's look at this two ring example. Okay, for one ring, the magnetic field lines are such circles. But if we connect the two, okay, we still have some circles. But if you look at here, there is a region in which it looks like as if the magnetic field lines are just parallel to each other. Now, if you would increase the number of rings, so here we have a ring, here we have another ring. The magnetic field, they are both rotate, the currents are rotating in the same direction. So the magnetic field lines have this shape. They're a bit deformed in the middle, but it's as if these rings, they're just constrain these magnetic field lines. Now if you would imagine another one over here, they will get even straighter. Now both are rings. Okay, there are some deformations close to the gaps. Close to the gaps, the magnetic field lines, it seems that they are trying to get out from those openings. Some of them manage to get out so that we still have ring-like magnetic field lines. In a sense. But nevertheless, there will be these magnetic field lines in between which will be just straight. Almost straight. There will be very small deformations. Now if you would imagine that you have infinitely many rings just next to each other, and of course the current goes out of the screen from the other side. Just imagine that we have infinitely many of them and that there is no gap in between. So there won't be any such rings. The magnetic field lines will not be able to escape these rings. They will be encaged, in a sense, and they will just go straight along this so-called coil. So these will be the direction of the magnetic field lines. This is our coil, and this is uniform straight magnetic field lines. This is what we call a solenoid. Now, how do they look like in actual life? Well, for example, this is a schematic diagram. It's just these coils. I mean, they don't have the space in between. Let me see if there are better images. For example, if you remember the demonstrations that we had on Tuesday, there was this ring demonstration. Those of you who looked at it from close by, they saw that there was this coil. Let's look for coil. Okay, this one. Actually, these are all our solenoids. They don't have these gaps, as in the case of the suspension. Now let's look at their magnetic field. How much magnetic field do they create? So this is our solenoid. We have already determined that the magnetic field line should be just straight lines. Now outside, if you look at this example, if you look at here, okay, the magnetic field lines on the out of this solenoid is created by these lines that can escape from in between. So if we have some magnetic field line here because it escapes from inside this solenoid. But if you just form them very closely spaced, no magnetic field line will be able to escape out of the solenoid. So inside you will have a straight magnetic field lines that are straight inside. Outside B will be 0. There won't be any magnetic field outside because magnetic field lines will be completely trapped inside our solenoid. Of course, this is the ideal case. In real life, the solenoids are finite length. There is still some spacing, although it will be negligibly small. So you do get some magnetic field outside, but it will be small. So inside we have this linear magnetic field lines. Outside there is no magnetic field line. Now we can apply the Faraday's law. This should be equal to mu0 times I enclosed. Now what kind of a closed loop should we choose? I mean, you see, in order to apply this Faraday's law, we first have to choose some closed loop. Like in the case of the Gauss law, we first had to choose some Gauss surface based on our general knowledge about the electric field and what it can depend on. In this case, we have to choose a closed loop. So the question is, what is our closed loop? What kind of a loop should we choose? A circle. Well, let's see. We know that the if we choose a circle, what kind of a circle? Around the wire, just like this. Okay. We can choose such a circle. Let's say this is our coil. We choose it or a loop out of it. But outside, magnetic field is 0. So B will be 0. B dot dl will be 0. So such a circle will not work. Now, what does straight magnetic field lines mean? They can be non-uniform. For the time being, we don't know whether the magnetic field lines are uniform or not. We only know that they are straight. Which is, well, if the magnetic field lines are straight, their density do not change as we move up or down. So it only means that the magnetic field, that the intensity of the magnitude of the magnetic field only depends on our distance from the center. It doesn't depend on whether we are here or we are there, because they both have the same magnitude, same density, because the field lines are straight. They are not approaching each other, they are not moving away from each other. So the magnitude of the magnetic field line, okay, the magnetic field lines, they tell us what is the direction of the magnetic field, and their density tells us the magnitude. The magnitude only depends on the distance from the central axis. It cannot depend on anything else. So if this is the case, now just like in the previous case, we have to choose a closed circle, closed loop, such that either as we move along the loop, we should be moving along a line which has the same constant magnitude of the magnetic field, or we should be moving in a direction which is perpendicular to the magnetic field so that there won't be any contribution. And that is, in this case, we can just imagine a rectangle. If we choose such a rectangle, okay. If we choose such a rectangle, On this side, we are moving in the direction of the magnetic field, and we are at the same distance from the center, so the magnetic field doesn't change as we go along this line. As we go along this line, along the top or the bottom lines, either we are in a region where there is no magnetic field, or we are moving perpendicular to the magnetic field. So in both cases, there won't be any contribution to that P dot dl. As we go along this line, well, the magnetic field is 0 along that line, so there's no contribution. So this integral will only depend on the magnitude of the magnetic field along this line, which is just constant. Again, let's put the signs A, B, C, D. Now this loop integral will be the contribution from A to B, from B to C, from C to D, from D to A. And the only contribution will be as we go from A to B. Because along this path, we are either in a region where we are moving perpendicular to the magnetic field, or in a region where there is no magnetic field. There is no magnetic field as we go from C to D. As we move from D to this point, the magnetic field is 0. As we move from this point to the point A, the magnetic field is perpendicular to our displacement. So all of these terms are just 0. Along this line, the magnetic field from A to B, the magnetic field is just constant. So we can just take it out of the integral. Now the magnetic field, let's just choose this axis to be our z-axis. The magnetic field is B in the z direction. Our dl, the sum of the displacement, well, let's assume that this is L. It is L in the z direction. So this is equal to B times L. From C to D. Well, let's go back. One slide. Now, if you look at here. Now, if you look at this example, and follow this magnetic field line. Well, this is just, as it's moving along the coil, there is this gap. It's trying to go away from the coil, out of the coil, but it fails because the other coil over here, other ring, in a sense, it just pulls it back inside the ring. But these ones, since they are very close to one of the rings, they will just escape. Although here they are in the coil, then they just move out of the coil. Now, when we close this gap between the coils, we are just closing this gap. The magnetic field lines, even these will not be able to escape. So if there is a magnetic field line inside, it will go just straight inside. It will not be able to go out of the coil, solenoid. Or you can look at it from another point of view. If you just take an arbitrary point over here, it will receive contributions from all these currents in one direction. It will also receive contributions from all these currents in the other direction. And since they are infinite, their contributions will just be equal in magnitude, and they will cancel each other. Eventually, of course, eventually there is an ending point, but let's just draw that to full scale. You say, this is our solenoid. It has an end. We are just looking at it very far away. Now, how will the magnetic field lines look like? This will be the shape. So just in this drawing, how many magnetic field lines you can count? There are 8 of them. 1, 2, 3, 4. Yes, there are 8 of them. 8 magnetic field lines, they spread out on all this area, but they're also concentrated in this very small area. So the magnitude of the magnetic field line out of my coil will be very small. Inside, it is large, it will be huge. Outside, it will be very small, negligibly small. In the ideal case, that you take the length of this coil to infinity, you see the magnetic field lines start from one point at infinity, and they just spread out everywhere. And I am at an infinite distance. So the magnitude of the magnetic field here will be negligibly small. And we are ignoring that. The number of lines, yes. Well, it dies away as 1 over r cubed, as we have calculated. This is just a dipole. From afar away, it's just a magnetic dipole of many rings. Well, in a sense, you can say that this is the fringing region. I mean, it's not really, not in the sense of a capacitor. We don't really have this fringing effect. The word doesn't really compensate. They mean the same thing. So here you have these magnetic field lines coming out, and of course, it's no longer uniform over here. They are spreading. But inside it's uniform. And that's what we are looking at now. We will discuss magnets shortly, don't worry. Now, which one? I mean, let's finish this one and then you ask your question. Other questions on this one? So this is what we have. Along that loop, B.dl turned out to be B times L. And the magnetic field, we defined it as B in the z hat direction. This is our definition of the magnetic field. Now, with this definition, this is what we have. They become important to in determining the direction of the magnetic field, because B can turn out to be something negative. Now, let's see. What is the enclosed current? Well, each one of these coils, let's say it's carrying a current I. There are n of them. This is the number of rings within a length L. Is it positive or negative? How do we determine the direction, the sign of the current enclosed by a loop? Take your right hand, rotate your fingers in the direction of your loop. My loop is rotating in the clockwise sense. Just curl your fingers in the clockwise sense, right hand. I mean, my loop is not like this, my loop is like this. My loop is on the plane of the screen. And my loop is not coming out of the screen. My loop, this blue line, is on the screen, so it's just rotating like this. So I'm just curling my hand, my fingers. One of your fingers should follow the curve at least. Not this one, this one. Don't break your arm. Okay, so it's in this direction. So if the currents are running in this sense, they are positive currents. If they are running in the opposite sense, they are negative currents. Now let's say the currents within my loop are running in this sense. So the currents are positive. Plus. There's no minus. Questions? Okay, this is our loop. Let's review. My loop, the blue one. This is my plane. The loop I have chosen is this, like this. It turns like this. Just take your right hand, curve your fingers in the direction of your loop. Yes. That is the direction that we assume to be positive for the current. So if a current is running in that direction, that's a positive current. If it is running in the opposite direction, that's a negative current. No. You see, if you look at this relation, this B dot dl, this is equal to mu0 times I enclosed, and here there is a loop. And also in your midterm, when you are calculating the potential differences, most of the time you ignore to specify which path you are taking. Here, once you choose, you are free to choose your path. I could have chosen my path to be rotating like this, or in the other way around. I am free to make that choice. But once I choose my path, and in which sense it is running, I am fixing the positive direction of the current. I could have chosen my loop to be running in the opposite sense. Well, let's solve the same problem using that convention. Let's finish this one, and then resolve exactly the same problem by just choosing my loop to be running in the opposite sense, and see what happens. True, yes. Exactly. Now, this is, at least with these conventions, this is my enclosed path. So BL should be equal to mu0 I times N, and hence the magnetic field is mu0 times N, where this N is the turns per unit length. Okay, it's the number of turns in my coil per unit length. Okay, before we knew that the magnetic field lines were just straight lines. It didn't depend on at which point I am along this solenoid. Whether I was here or over there, they should have the same magnetic field. But now we also know mu0 and I. Now we also know that the magnetic field is uniform. It has the constant same value wherever you are within the solenoid. It doesn't change. Now let's assume the second solution. Let's look at the second solution. And B, magnetic field itself is this one. Okay, this is, I just changed the direction of my loop. You are free to choose whichever loop you like. You are free to choose whichever orientation of your loop you like. It's completely up to you. Now again, let's calculate B dot dl. Let's calculate B dot dl. Again, I will divide it into various parts. Now this time I'm going from A to D, from D to C, from C to B, and then from B to A. And just like in the previous case, as I go from, let's say, B to C, no, it's from D to A to D, or from D to C, or from C to B, the first three, they are zero. Either the magnetic field is zero, or we are moving in a direction perpendicular to the magnetic field. This is zero, this is zero, this is zero. And remember, B is B in the z hat direction. This is equal to, B is just constant along from B to A. B is just constant because my magnetic field lines are just straight. B dot from B to A dl. This is B in the z hat direction. Okay, this integral is nothing but a vector pointing from B to A and has the length, this length, which is L, and that vector is minus Lz. So this is equal to minus BL. By just changing our orientation, this integral changes sign. Now let's look at I enclosed. This is equal to, again, n times I. I have n coils, each one carrying a current I. The currents are all in the same direction. Now, is this a positive current or a negative current? Once you choose your orientation of your loop, the positive direction and the negative direction of the current is fixed. Now, just wrap your fingers in the direction of your loop. This is our positive direction of the current. Since this is the positive direction of the current, and all my currents are running in the opposite direction, they are all negative currents. So I enclosed is minus Ni. So this B times L should be equal to mu 0 times I enclosed, which is minus Ni mu 0. So again, we get B is equal to N mu 0I. Changing the orientation of the loop didn't change our result. It shouldn't change our result because the choice of the loop is just a mathematical choice. It's not changing the physics. So whichever method you choose, whichever loop, whichever orientation you choose, the final magnetic field should have the same value. In which one? Okay, here I define the magnetic field vector. Of course, in the exam, if you are asked for the magnetic field, that is the vector, and if you don't write this final expression, you will lose points. Okay, there's another point. Now, here, I chose such a loop. I can choose any other loop. I can choose, let's say, another loop on the other side. And then I will obtain the magnetic field. If at the end, I will not be summing these magnetic fields. Because again, back to the midterm, there were these infinite plates. Some of you just calculated took two different Gauss surfaces corresponding to two different plates, and then you just sum the results. Just using all of the configuration, we already have determined that the magnetic field outside is 0, inside it should be, the magnetic field line should be straight lines. To reach this conclusion, we already used all the currents in our system, not just these ones. All the currents in our system led us to the conclusion that all their contribution led us to the conclusion that B here is 0, B here is 0, the magnetic field line inside the solenoid is is just straight lines. We are already using all the currents, not just these currents over here. The final, the net, the total magnetic field, it should satisfy this equation. B dot dl should be equal to mu0 times I enclosed. That is, the total current should satisfy that one. So we don't need to add anything here. Now, of course, I could have chosen some other loop on the other side. It will still give you the same answer. It's exactly like the Gauss law. The only difference is Gauss law, you are integrating the electric field over a closed surface. Here you are integrating the magnetic field over a closed loop. That's the only difference. Other questions? Now, when we are defining the Gauss law, okay, that's from the main definition, the B dot dl. Here you have a closed loop, which you can orient in whichever way you like. It's up to you. You can choose this orientation, let's say. But if you choose a given orientation for your loop, the current running in one direction, this will have I larger than 0, and the current running in the opposite direction, this will be I less than 0. And if you want to use this law, you have to assign signs to your currents. They should be positive or negative depending on which way they are going through your loop. And the positive direction and negative direction has to be consistent with the orientation of your loop. They're not arbitrary. Okay, there are two things that you can choose. The orientation of your loop. You can just run around your loop in this sense or in the opposite sense. And you can choose the positive and negative directions of your currents. There are these two things. And these two choices should be consistent with each other. They are not free from each other. You are free to choose any one of them. Either you choose the positive sense of the current and the negative sense of the current. But if you choose any one of them, the sense in which you go around your loop is fixed. They are not independent of each other. Okay, so let me just erase these ones also. Okay. So in this one, you cannot see this portion of this wire because this wire is blocking it. So this wire is in front. This wire is on the back. Other questions? In that case, you just need to go to your Biot Savart Law. You have to integrate this one if you have an arbitrary shape. Just like the Gauss law. Gauss law is true in all circumstances, but it's not practical except that in cases in which the charge distribution is quite symmetric. Biot Savart law is similarly, the Faraday law is always valid, but it's not so useful in cases where you don't have too much symmetry. Now, we had applied the Biot Savart law in two cases. This solenoid, which due to the symmetry, the magnetic field lines inside are just straight lines. And then we also have applied it to an infinite plate. Again, it's quite a symmetric system. If you don't have this symmetry, you cannot use Faraday's law. And you are back to using the Biot Savart law. You have to sum them all up. Other questions? Okay. This one. Now here we just said that, okay, while you are getting ready, just looking at these two different contributions to the total magnetic field, they are quite symmetric, meaning that the Z components are in the same direction, but the X components are in opposite directions. So when I sum them up, the X components, they just cancel. The components vertical to Z. So I'm not writing them anymore. The Z component will survive, but there's also the component perpendicular to Z, but when I sum them up, it will give me 0. It should give me 0, that's why I'm not keeping track of those components. Okay, so you have these two wires, they are not parallel to each other, they are perpendicular to each other. So I'm asking for the direction of the force acting at the point A and acting at the point B. I'm not asking for the net force. Just imagine a small segment over here. What's the direction of the force acting there and acting here? This point B is not the magnetic field. Well, I'm just asking for the direction, not the magnitudes. They're on my wire. They're just 2 points on 2 small segments of my wire. I'm just asking for the direction, not the magnitude, not the sum, etc. Just answer A, answer B.